Okay, let's try this again, maybe with a bit less distraction. So, um, there is this protocol called Simple Certificate Enrollment Protocol, and it has the task to, if you already have a certificate in your public key infrastructure and you have a server that speaks the protocol, you have a client that speaks the protocol, they can communicate over it and initiate renewals or even initial requests for certificates. And everyone that has already worked with such certificates knows the basic gist. For everyone else, here it goes. You may have seen this SSL stuff where there is a certificate behind, and you have a domain and all kinds of other parts. You also have an expiration date, and normally you are around 1 to 2 years with this. At least that's what's the recommended time frame. And if you are operating some kind of infrastructure where you have many certificates, it can get kind of overwhelming to manage them all by hand. And so there exist these management protocols. Well, thing is, there exist implementations, and actually part of my bachelor thesis was working with one of these implementations, but the problem is they are command line clients, or this was a command line client, and I particularly disliked having such a command line client because there was a Perl script written around it that just called the command line, and especially if you have like private keys, this is not something you want, that maybe you have to see a private key and put it on the hard disk so it can read it again, or even there are passwords that the command line client doesn't support passwords, so the Perl script would just decrypt it, run the command line client and delete the file again, but still there was a file on the system that contained the private key in a decrypted format, and well, there are basically a lot of other issues. So I started working on this library that implements the protocol in C, but does not require you to use a command line client. You can use any bindings you like, and this is currently in the development phase, but we actually already have a working Perl binding, not created by me, but by a friend of mine who's working with me on that. And yeah, this already works, at least from what I saw. It used to work. I think it still works. And basically, I have no idea. Okay, I have to look here. It wraps around the C code some Perl stuff, and now you can call from Perl script here with your PAM encoded data and kind of create the messages you want to send. And that's the basic idea behind this. There are kind of like two more or less separate components in this library. The first one is the messaging part, or the protocol has two parts, and the one is creating these messages that what happens here. This is described in the standard here, these secure message objects. So you take all kind of cryptographic objects and information and stuff it in this box and get one long PKCS7 message. Doesn't matter if you don't know what that is. And then you can send that to the server. That is actually part 2, communicating with the server or receiving data from a client and creating a response based on kind of policy and how you want to create the new certificate that was requested. Yeah, that's the basic idea behind the library, and because we think that the communication process is not something a library should decide, because well, the protocol even tells you that you have to use HTTP, and it tells you how to call this and how the headers and so on have to be defined, created, set. Okay, let's say the headers have to be set, which values have to be used. But how you send the request, I think that should not be something the library decides, because especially if you have multiple languages, like you may have seen that there exists the idea of creating a command line client, a Perl client, and a Python client. And the command line client should just replicate the old tool, which was called SSCEP or SSCep. And yeah, this was the original tool, and the command line client should replicate its behavior, but maybe extended by features, and of course use the library instead of all the built-in stuff that only works together, because really a lot of code in this, and that's the reason why a rewrite is easier than modifying this program, is that the main function is extremely long and takes some weird assumptions, and it would be really ugly to just, I don't know, rename the function and make a library out of it. That would be bad. So yeah, instead we do a rewrite, and we're actually pretty far in the development phase. Right now it should be possible to create most of the functionality already inside the original tool, and that's like the first goal, to kind of have a drop-in replacement, so you can create a program that behaves exactly like the tool before, and you can just drop in the replacement, and then you can start developing more fancier stuff, like calling it from Perl if you have a Perl script, or from Python if that's what you want. Yeah. Thing is, right now I'm working on engine support. To get an idea for engines, this is the only dependency for our library is OpenSSL, because it does all the cryptography stuff, and we just kind of call the right functions at the right time with the right parameters, and this message object PKCS7 drops out. Yeah. And OpenSSL has a cool feature called engines, where you can take the private key operations and some high performance demanding operations, etc., to an external device. And for once it allows you to speed up your computation if you have a dedicated device that might be faster. But the more interesting part is that you can actually store your private key on this device, and these devices are often called hardware security modules. Would be like the prime example of why I'm doing this, because inside a hardware security module you can store your private key and prevent someone from accessing it, even if they have physical access. Because the idea is that depending on the way you configure it, you can build it in such a way that even the user can't access the private key anymore, only request operations on it, with it, authenticate them, kind of like having an oracle of your own key, but you can't get the key. So you send a request like encrypt this, sign that, and it does that. And this is like you already heard, sign and decrypt. It's mostly the asymmetric cryptography, so RSA, for example. Yeah. And the idea is that if you load such an engine, OpenSSL can transparently relay all the relevant operations to this engine. And from our point of view, this is loading a private key, get a reference to it, without actually having the private data in memory in our library, because we assume we cannot access that. And then we define OpenSSL, or tell OpenSSL to use our engine that we just configured as a default. Always use it. There are other ways, but that's kind of the approach we're using right now because it is easiest. And we tell it to use this engine throughout the code. I can show you this part. Let me switch this over here. So this is the most important part, and you can ignore most of it because these are just some requirements. This is important. I create such an engine object here, and then I make it the default. And all the other stuff around and some other stuff that needs to be done are configuring the engine. But let's just say you get an engine object here, you make it the default for all operations, you start it up, and you can use the engine now. And the funny thing is, the really nice thing is now that it will all automatically forward the correct operations to the engine. And in a use case, or let's just say we take a look at this, because down here we can see, yes, how such an engine is loaded. So these are the unit tests, and this above here, these two lines load the engine, so they hop into this part of the code. And well, it's not that important what exactly is happening here. Just know that I'm using the PKCS11 engine and interface as my test basis, because I could set something. I just told you they are hardware security modules, but I don't have one lying around because they're fairly expensive or contained on these smart cards that you may even have yourself. Anyways, this interface is actually the smart card interface, but it's emulated right here. So it's just software running in the background libraries and all kind of stuff. Yeah, and here comes the real magic. I tell OpenSSL now I have an engine and I want a private key from it. So this is my engine object, and this is my identifier. And you might notice that typically, if you have ever used OpenSSL's API, you provide file names when loading keys. And in this case, we don't. We actually provide something called a slot. This is like, imagine you have a card reader with multiple slots, so you could have multiple cards. In our case, this is always 0 because we assume we have just one card reader and a key ID, which is 1. And that's just something you define. When you add the key, you either get back a key ID or you set one yourself. So we tell OpenSSL to give us this key, and OpenSSL actually hops into the engine and tells the engine, give me that. And the engine does whatever it needs to do to create a key object. And now comes the real magic, because if you have ever coded a bit more deeply in OpenSSL, you see this EVPP key, and you might have seen it already. It wraps around either a public or a private key, and it's completely transparent. It is used for RSA, it is used for DSA, it is used for elliptic curves, it is used for all kinds of keys, and it can also wrap around engine keys. So right now we have a key here that I may be able to show you that if I look at the right. Yeah, let's see this here. I hope you can all read this. This is such an EVP p-key struct, and we see that this holds parameters for RSA or DSA or Diffie-Hellman or elliptic curves. And here you can save an engine, and I don't know, the type probably tells you which p-key type this is here, and then I know this is an RSA type, so I can take a look into this, and there we see an underlying RSA object. And if you're familiar with this, the N is the modulus, and E is the public key, and D, P, and Q are your private parameters. And the other stuff, these are just intermediate parameters. You'd actually just need P, Q, N, and E to compute D and these intermediate values. This is just like caching them. Never mind though, we could try taking a look into such a key. I don't know if that will work right now, but yeah. So even though this is an engine key, this wasn't set. This is not necessary to set an engine, even though we are using one. But what you can see here is that only N and E exist. There are no private parameters. And as this was called a key, this is a private key. So the public part of this would be the decryption cert. So a certificate is a public key with more information and security features. And the key is the corresponding private part. And what's important here is to notice that there is no private information in our private key because it's all inside the engine. And that's what this math block tells us. Let's see if we can take a look into that, because that's... No, what did I do wrong? Oh yeah. So yeah. So this is the struct, and these are the versions, the values, sorry. And we see all kind of function pointers, and I don't think we can see this here very well. I won't go into depths now what this means. The thing is, these functions have been registered and replace the original functionality. So if we now want to perform an operation with the private key, one of these callback functions is used. They will hook into the engine will know what to do and return the result. And that is completely transparent. The interesting thing, as I mentioned before, is I now have such a key object. I can work on that with that, and I don't have to specify the engine anymore. So that's really not important at this point, that I have an engine, because, and that's now why this is cool, because I can now hop into my original code, and this is where this message is created that I was telling you about. Let's just say I want to make a request to renew a certificate. This is so-called PKCS rec. And I give this certificate signing request, this function. I give it a certificate that is valid, that is mine, that I have a key for, and I can use that key with that certificate to create a signature. This signature will authenticate the request, and because the server verifies my certificate, my signature with this certificate, he knows that I made this request and may, if he wants to, approve this CSR and create a response. We get to that. Then I use this encryption certificate. This is a certificate from the server. I encrypt my request with it, and the server has the key and can decrypt it, so no one on the line can read the actual content of this. Yeah. Let's see. This is the relevant relevant part, right? We have this EVPP key, and now we want to use an engine. Well, as I said, as you saw, if I get a key like this, I can pass it here because it is the correct type. Let's see what happens. I pass this around to the init function. It's about above here. That takes the key, and now we go into OpenSSL, because I now tell OpenSSL to create a signature of my PKCS7 object. I don't sign yet, I just initialize this. But I now have given my key to some weird PKCS7 function. And then I store this in a variable I pass around to work with. Now let's hop into the, I don't know, let's say, yeah, we go into our core function that is called PKI message. There we go. Yes. And this is the variable, is it? Wait a second. Yes, this is the variable containing my relevant data. I'll give you a second view that should make things easier. Yeah. So this is the P7 data that contains all the parts I need to pass around between the functions. This is just an internal variable, but here's our signer info, which is the only part where I ever passed the key in. Okay, so we need to follow that now. And that is actually here used as well. And it adds an attribute, a signed attribute. Okay, this is done a couple of times. And this is not really not the most interesting part. No, that comes actually, I'm sorry, I need to hop around in the finalization function, because now I call this data final, and this works on the full PKCS7 object. So this signer info is part of this P7 object, right? And now comes the data final part. Now comes the magic, because inside here somewhere the private key will be used to create the final signature. And that is where we want the engine to start working. That is what we need to test, and that's, now we come to that part. That is where what I'm currently working on. So I have my unit tests, and I wrote a test for a cert rep message, which is a response. That's not important right now. What's important is that I get such a response, I unwrap it, and I get my response information back. And the most important part would be this, a certificate, a newly generated, created certificate. And to get that, I get encrypted content, and I have an encryption key, and that is in my unit test stored in the engine. So this key here right now is contained in an engine, and I want to run this unit test with the key in the engine. And if I hop back into, yeah, I don't know where I want to hop back. So this is a test I'm currently running that should pass. It passes without problems when no engine is in use. And now I'm trying to use an engine to see if the same thing works. And as you see the GDB open, it does not. And here we have the backtrace and can see, let's look at the correct part here. So this is the function I was telling you. This is the test that's running. It hops into the unwrapping in the encrypted part, and here starts OpenSSL. So PKCS7 decrypt is not what I have shown you before. I know this was not cleverly designed, but that's the way it is. So here it goes. I pass in the key, it goes to the decrypt function. This is a lot easier to explain than this kind of signing stuff that goes through so many layers. I pass it a key and it tries to decrypt. And this decryption fails, so I took the line where it fails and set a breakpoint. And now I'm trying to figure out what's going on here. I have no idea if I'm going to even remotely be able to find out what's happening, because now we're diving into OpenSSL and that is always ugly. So let's start with the first function here, and I'm going to explain these parameters and why they are set and to what and what they contain, at least to the point I understand them. Okay, so 585 in the smime pk. Oh, I see I have this open here. Let's say 585 would be around here. So this is a bio read. This is not the part that does the actual work, that has to happen somewhere else. So where is our key used? Right. It's a checkmate, that's okay, and then it's calling data decode. Okay, this is happening in the pkcs7 doit function, where I need to close some of these to get a bit more overview here. Let's see, there we have it. So we have this data decode. I think that's what's happening here. Yep. And this, oh, right, I'm not going to tell you what all these variables do. You don't want to know. Not right now. So long function that gets our key, and this key I'm going to follow in this function now to see where it does its magic and how it is probably attached. Okay, so here we have a condition, and I'm going to tell you we pass in a certificate, so this is not null, and so this is what's going on. And this one has the p key, so let's see if it is used somewhere else in this function. Does not look like it, so we need to look at this one. Yeah, this is what happens when you work with OpenSSL. You work yourself through weird function names, weird file names, undocumented code until you see that you create something I have not yet found out. So EVPP key is the name of the type of our key. CTX stands for context. And normally you get this when you like create a hashing function. You create a new context, you dump data in it, then you finalize it. This data dumping is called updating. Then you finalize it and you get your result back. And I'm guessing something like that is happening here too. So the p key is passed in here and never used again, because now our relevant reference is this context. And we have an initialization function, then tells it to decrypt. But I cannot tell you why these functions are all necessary. I just see that this seems to be doing the work. And if this worked, right, it gets first back how much space we need. So it calls this twice, and on the second time it has allocated enough memory, and then seems to be filling in the data. What did it allocate on EK? So that's right. This is, could this be? Okay, so Yeah, I think I need to say something about the PKCS7 structure here. Otherwise, we won't be doing any progress. Let me hop into this and take a look at some. Okay, I'm going to show you one of these search rep strings. Am I going to be doing this? Yes, I am. And I need to get an output so I can give you a nice look at it. Here we have it. Let's see, what did I have? Search rep success string. There it goes. Okay. Yeah. Okay, we ignore all that and take a look at this. This seems to be what I just wanted to have. And so this is an ASN1 data structure. Never mind about that. This is, I think this is relatively easy to read, but we now need to work ourselves through this to find out what's going on here. We have a lot of interesting information. For example, we can see here, you see this DE ASDF is what I typed, CA. So this is all in all. This is here, envelope data. So we have here the country name component and so on. If you look at this, here is the country name. Is it somewhere in here? No, it's not. Okay, let's look at this. This is nicer. Yeah. Here we go. So what we see here are these fields. So there are different keys used here, but the one you will always find is the common name. Now I need to close this to be able to look at this. This is not really important for us right now. So this is just to show you that here is a certificate or information about a certificate is contained in here, and we can use that. But that's not important right now. We should close this up and take a look around to get a feeling for what's going on here. Okay, so we're looking at the outer PKCS7 now, which contains a signature. It's not interesting. What's interesting is the actual content. Okay, so this is not going to be easy in this way without taking a look at the PKCS7 standard. Yes, yes, you have to read standards now. No, you don't. I have to. Okay, so what we are looking for is the knowledge that this is signed data, and where did I have the envelope data? And inside this envelope data, there is my content, and there is something encrypted. We are going to look at the structure now in such a way that we can determine where the encrypted content lies. And because I always lose track of stuff, I don't know right. Because you might know that asymmetric cryptography is slow compared to the symmetric part. So RSA is great because it allows us to have this asymmetric operation where I can encrypt something for anybody. So I have the public key, I encrypt it, but I can never decrypt it. Only they can. And signatures work the other way around. I can create a signature, everyone can verify it, but only I can create it. That's very important. But it's slow compared to the other algorithms. We have like a AES or triple DES or something like that. So this symmetric cryptography is a lot faster. And then, of course, the idea is to only encrypt the key of the symmetric cipher, so maybe AES, which is fast, and only this relatively small key is then encrypted with the asymmetric cryptography. So what actually is happening is that somewhere in here, and I guess it's this, is the encrypted version of my symmetric key that I want to use to decrypt this, which is our actual content. Is it? I think it is. Okay. So we want to have that, and to get that, we can see here this is RSA encrypted data. I think, yes. Okay, so this should be decrypted using our private key, and that's what I wanted to show you. I wanted to show you that at the point where it's saying, what was it, right here? Yeah, right, the recipient info. It contains, I think this might be all of this. I don't know to which depth, but I'm pretty sure that this is part of it. And this is the so-called content encryption key that, as I explained, encrypts the actual content, and we have to decrypt this. And I think that is what is happening here. So here will be the encryption key later. And as I'm talking about this, I do realize that I have no idea. We took a look at this function here, and we know that this is not where the problem occurred. It happened here. So way later. But we can see that this is the common variable, one of these bio structures, and I'm not going to explain a lot about it, just you can dump data in it and read it out, and you can have kind of data processors in between. So what might be happening is that instead of directly decrypting, there is a data processor attached that that decrypts the data on the fly when we read it. We get it decrypted live, but only if we start reading. It's never decrypted beforehand, which is handy, but now makes debugging a little bit harder. Okay, sorry for the interruption. So let's see. Maybe it's interesting to get a hang how this is constructed. So we go back here to this function, right? And we have a return value. So let's look at when and how it's returned. Oh, this is a long function. No, it's not a return value. It's not. Oh, it is. Just quick. Okay, so the out value is what is returned. Then let us look when there. So it seems to be set here and here again. So these might be different cases. As you can see, this is horrible, horrible code. It's we are lucky we actually have a comment in it, and sometimes these error messages can also help us decipher all this. But please take a look at the indentation here. It's a bit crazy and doesn't really follow a clean style, but we'll manage around that, I think. So This out bio seems to be set. Okay. So it is, I don't know why it is set here or what it does. Maybe I'm slow. Where was the key used? Much later, right? Right. Okay, let's try to build a connection between that. So it decrypts this and gets the key back here. It uses this key. Oh, this might be interesting. It uses this key and nice. So we have some comments. Anyway, it is put into the cipher context. So this is where the actual decryption may happen. Yeah, here. Right. This is how you decrypt stuff when you have a symmetric key, I think. So it's initialized, and what we get back, it initializes the context, but I'm not so sure. Ah, here. So we have this crypto context and we have the bio. Yeah, and now I know that this is the bio working with the cipher context, but this cipher context gets the actual value of our content encryption keys. So this seems kind of unrelated to our engine stuff because this is symmetric cryptography. This should be well beyond the scope, at least of our key part. What might be happening is that this still hops into the engine, but I don't think that it provides. I'm not even sure that an engine can really provide symmetric cryptography support. I don't know. So let's see the manual page for this one. Yes, it has one. That's great. Okay. Decryption. Let's see, its signature is it gets a cipher context, gets the type, which, okay, I don't know. You can, oh, you seem to be able to pass it an engine. That is what happens if you want to do it explicitly and not set it globally as a default, but we don't do this here, so that doesn't concern us. What's interesting is this one. A key, then you can get an IV, and then some kind of parameter. And if we look at that now, then this is the key without an IV. I don't know why, because we normally would have an IV. So I'm not sure about that. Maybe this is set somewhere before. So here's some initialization as well, but it doesn't set the key here. Here it, oh, I don't know what it does here. Okay, wow. I'm not actually, I'm not really sure where the IV is coming from. But we ignore that now. What's important is that this unsigned char key here, that is already the decrypted version. So our key has been used, and that is actually, that's an important important insight right now, because it does not seem to be, it does seem to be an engine problem, and I'm going to show you why. Let's just run this. So I am running this test code, and I'm only running this function right now. And let's run it. So we see that this test failed. And we also have an error message. That happens in these EVP enc C. That was what is happening here. Decrypt final. Interestingly, it's called EVP, and I thought this was only for asymmetric cryptography. So maybe I'm wrong. And this, but I think that at this point we'd already have our asymmetric part done. We have dealt with it. Let's see. Okay. So we pass in our private key. To this decoding function. It takes it, and this should be this function, right? Yes. Takes it and uses it to get the encryption key. So if I get this right out of this, we should get our encryption key. And that encryption key is then given to these cipher initializations. So let's say okay, I'm more interested in the general description of this high-level interface to symmetric cipher. Yes, that's what I wanted to hear, because then we don't have an asymmetric part here anymore. That's not possible because it expects an actual key here. And now let us see the data. How is the data given in? Because that's also interesting. So what we are doing is we are calling this PKC7 decrypt function, and this is where our data is in. That's fed to, okay, so this is not text. I think we are passing in binary. So we are here. It writes, yeah, right. Exactly. This is where the data is contained. This is where our output goes. So this is where the data comes from, and this is where it is written. It's taken from this, it's read from here, and oh, surprise, this is exactly what fails. So this is the bio we get back from our decryption part, and that was, I feel like running circles right now. That was this one. Okay, let's first figure out why there are two assignments. Oh, right. So I need to explain a bit of this chaining. What I said before, this on-the-fly decoding is actually what is being done here. The bio is taken, and if we already have one, we just put another one to it, so kind of like chaining them. And if we don't, then this is our first bio and we don't have a full chain yet or something to chain it on. So this is our first part of the chain. And what is it? What is this ETMP? It's the from the I don't know. Okay, let's see. It is the other way around. This is a cipher bio that has a context that we retrieve. So this is not used anymore. So this is our context. This is interesting now, because what we put on it is the this is the cipher object is retrieved from the PKCS7 structure, so it reads in where is it? Here. It reads this field, and in this field it says DSCBC. You can see that. I can't point to that right now because then the field goes missing. Oh, can I? I can't. Okay. So it says DSCBC, which is data encryption standard. Let's not dive in too deep. Just know that this is how this ETMP with this context is created. Then we drop in EVP cipher, right? This sets the cipher, what I just said. Right. So it drops in the cipher. Then, okay, I don't think this is important. This checks the key length of a cipher. Okay, it just says it's a defense, so we can ignore that. Just uses a random key that wouldn't work. And here we get to the real meat. We use this okay, we just check the length here, and then we drop it onto the cipher. And then we have configured it, and this is like, now it is prepared to be decrypted. Next step is to take a look at the next part that is given to this out part. That would be this bio riddled with. Okay, nice. The question is now, what is happening here? Because that is the next part that is attached. I'm not sure, but it seems to be just a bio that is a memory buffer. But I'm not sure why. I'm not sure if this is important. But let's keep that in mind. That seems to be already it. Did I miss something? I thought this happens twice. Right. I should have taken a look at this as well. Yeah. What's going on here? Signature checking. Oh, this is nice. Could it be that that the check of the signature is also part of this biochain and might be part of the failings. So it creates a bio that is called biofmd. So MD is message digest and it stands for these hash functions that are then finally used for signature verification. Okay, so here we have the digest that is actually in use, and we set that here, but I cannot exactly tell you how this is signature verification right now. It's this MDSK. Okay, let's see. I think we need to go back to our message C, or the static functions in it. We need both, because I think this is completely irrelevant, this MD part. Because when a response is unwrapped, the libscep unwrap function is called. Where is that? Not here. Okay. Wrap. Yeah, there we have it. It is called, and it gets this PKI message, gets the signature, it verifies this at one point here. So here's the verification part. Signature is already verified. And now the signer info. I want to know at what point. So in this message is everything. So at some point we have to extract the data from it. I just can't find this part right now. Here it says handle encrypted content, which seems like the part. What's that? Yeah, here's enc data. Where's this coming from? Ah, right. The verification function also handles giving us the correct data. That's why I couldn't find it. Let's see, this would be here, I think. Verify, right. So, yes, we verify that and we get back a bio that contains the inner data. So, to take a look at this again, what have we here? Here's signed data. And then somewhere inside here it says, here it's data, and then envelope data, and this is the data part. So what the bio has is all what is contained in here. And if I did not lie, then the signature is somewhere here. So yeah, this looks a bit like possibly a signature. I don't want to go into too many depths when I look at this. Certainly want to be sure to not be. Yeah, okay, so inside this bio is what we have, and that contains again an envelope data, so it's really nested. And then we are back to our part. So the bio contains this, has no signature anymore. And this bio I have here is what this enc data is what this enc data is. Then this is given into a new PKCS7. So this is read again as a PKCS7, but as only the inner part, as I told you. We could also print that and we would see that. Should we do that? I think we do that now. No, this is not what's going to work. It's called PEM write PKCS7FP, I think. I'm not sure. Let's see. Nope. Could it be PEM write FP? PKCS7? No. PEM write PKCS7, and that would PKCS7 write that. Okay, right, no FP. Yeah. So PEM write PKCS7, then we pass in the FP and this one. And now let's see if we can run it again. But we did not build. Yes, that's it. That's the inner content. And if I'm not completely mistaken, this should be the exact same thing we were looking at. Just the inner part. Right, the envelope data. So everything from here. That's great. So we know at this point signature has been verified. And we have our content encryption key. And it's hidden inside this structure. And because now the only asymmetric crypto operation is extracting that key, and I think we can be sure that this has already happened. So when we take a look at this, so the reason I hopped out of this was because I wasn't sure if this would need to be checked, but it wouldn't. So this is not happening. The other part, I'm already very sure that this has nothing to do with the private key anymore. This is only this encryption key. So let us, yeah. This is the part where I now need to find out why this fails with an engine, but not without, even though no asymmetric cryptography is performed. And for that we head into the engine itself, and it's called something like this, right? Now you can see how such an engine is defined for the interface. So these are parameters you can set. These are commands you can pass to the engine, and it will sorry. So you can define several commands to set these parameters to alter the engine behavior from the default. For example, what we are using is this CMD pin to set globally the pin to be used when we want to retrieve private keys or have the engine operational with them. We need to set such a pin. There are several ways, but this is for our purpose right now the easiest. Yeah, and this is the function that is called on initialization. So when engine init is called, and these operations are executed. And what it does is it sets several cleanup allocation functions. It has an RSA method, it has a DSA method, Diffie-Hellman. It has a function to load keys. It does not seem to have anything else right now. I cannot not see any function that would drop us into this. But there's a different option. I now realize that, because this decryption might fail if our content encryption key is already broken. So let's check that. How can we check that? We need to take a look at the actual key, what it is, and then we need to check if with the engine the same key comes out of there. And I think this is not something I'll get to do today. Not in the full way I'd like to do that. So yeah, I think this concludes my actual first Twitch session that I'm pretty sure no one will watch. But it was nice anyway. So I hope you learned something. Or, oh well. It's it's not easy starting on OpenSSL. So I had my problems today as well, and it's a funny Safari experience going through OpenSSL's core code, and we actually hit the nice parts today. I think I have seen worse of this code, and yeah. If you have any questions, please let me know. If you liked the video, please let me know. If you didn't like it, let me know as well. But we're on the internet, so I guess if you don't like it, you'll flame me anyway. So, I wish you a good night, have a nice evening, and see you